Okay, so what we're working on today is called optimization. I'm gonna go ahead and let you read a problem. Yeah. Okay. So, what are we trying to find in this problem?
Largest possible square you can have, in which all the squares have to be the same size.
Okay, we're cutting squares, so we want to know the size of the squares so that we have what for our box when we make it? The largest volume possible. Talk with your pod. What are some synonyms for largest?
Immense. Enormous.
Pod 4, what's a synonym for largest?
Enormous.
Okay, pod 1? Maximum. Pod 2, have we been finding maximums using calculus? Oh, we've been finding have we been finding minimums using calculus? Yes, yes we have. Okay, so an optimization problem is just a word problem to find a minimum or a maximum. Okay, don't write this down, I have it written down for you.
The area of each percent.
Now, last year in pre-calculus, you did some linear programming to find minimum and maximum values, but that was restricted only to when you had linear constraints, okay? Here, the door is wide open for our limitations, okay? So, here's our problem. They're going to give us some information, and they're going to tell you, maximize this or minimize this. That tells you, hey, we can use a derivative to help. All right? Now, when you read the problem, just like with related rates, I'm going to ask that you draw a diagram. Okay? You're going to have to label potentially some variables, potentially some measurements. Okay? Determine what equations you will be needing. Okay? When they say maximize this, you're probably going to write an equation like that. Okay? There are going to be some problems where you'll need two equations to help you. Okay? Related rates, we wrote equations that were implicit. With optimization, since we're finding minimums and maximums, we have to write an explicit function. So we could potentially need a second equation to write our first equation in terms of only one variable. Okay. And I'll show you what I mean when we get to a problem like that. Okay? It's important that you identify what you are trying to optimize. If you are trying to maximize volume, then we're going to want to take the derivative of the volume equation. Okay? If we're trying to, whatever we're trying to optimize, that's the equation we want to focus on. Okay? Like I said earlier, we want explicit functions. So if you have an x and a y that you've labeled, you're going to have to use a second equation to rewrite y in terms of x. Okay? It is important to think about domain. Okay? If you get, thank you, a negative number, and that negative number represents a side length, that's probably not okay. All right? We need to understand what values will and will not work. Okay? And then we will use the first derivative test to find minimums and maximums, okay, depending on the problem. Now, it is important that you show me the work for the first derivative test. okay? You don't just get a critical value and assume that it's maximum, okay? You have to actually make sure that it is, okay? So we have 3 examples that we're going to go through today. You will get a homework assignment tonight, and then tomorrow we'll continue to work on problems. A lot like related rates, we just have to be exposed to different types of problems. Okay? So we will come back to the one that we started with. Okay. We have a sheet of 12 by 12 cardboard. Yep, cardboard. And we're going to cut squares out of the corners to make a box. Okay. So here's our visual. We have a 12 by 12 piece of cardboard, and we're going to cut squares out so that we can fold up those flaps and make a box. Can you visualize that box? Okay. Correct. It's an open top box. Okay. All right. Do we know how big the cuts are? No, that's the whole point of what we're finding, right? So I'm going to label these cuts as x by x squares. We know that they're squares. That's for sure. Okay. So we want the largest volume possible. So let's write a volume equation.
Could the following students please report to the competition gym for their yearbook photo? Titans Unite, German Club, Circle of Friends, and Forensics. Again, that's Titans Unite, German Club, Circle of Friends, Forensics. Thank you.
Okay. So, volume. Logan, how do we find volume of a box?
X squared. Well,
Well, let's, just like in general, if I have some sort of box. Well, we don't know that it's a cube. It's a rectangular prism. Let's just ignore this picture. How do we find the volume of the box?
length times width times height.
Thank you, that's what I was looking for. Length times width times height. Yes, we have a square base, and so that's going to help, right? So, our length and our width are the same. That's what you're kind of trying to get at, right? Okay, Joe, what is the length of this box once we fold it up? Joe says 12 minus 2x. You agree? Okay. And would that be the same for the width? Okay. So for length times width, we have 12 minus 2x. 12 minus 2x. So I'm going to say 12 minus 2x squared. So that's length times width. Okay. Alex, what's the height of our box? X. So here is length times width times height. Okay. Now, Q, is this an explicit function?
Yeah.
Yes, it is. There's only one variable, so we only need this primary equation. We don't have to write a second one. Okay. Since we're trying to maximize volume, what should we? Oh, first, I skipped a step. Sorry. We need to think about the domain. Okay. "30-second conversation, you and your pod decide what can X be, or what can't X be. Talk about it with your pod.
Must be greater than 0 and times must be less than 6. It can't be 0 minus 12 That's be not your value. Yeah.
Okay. Larry, what do you think?
Over 6. 0 to
maybe 12 times 12 times 12.
Okay, Larry, this is what I want you to think about. We're talking about x, right? So what's the biggest square we could make until we cut too much out? If our box has length,
6.
there we go. X has to be between 0 and 6. Otherwise, if we're past 6, if x is 6, that's cutting 4 squares, and there's nothing left. Okay. All right. So now we're going to take the derivative of our volume. Okay. You can do this a couple different ways. We can use the product rule, or we can multiply it all out and go from there. Product rule. So our derivative, let me do a different color. Our derivative. Product rule. The derivative of the first is 2 times 12 minus 2x to the first times the derivative of the inside, negative 2, times our second function. Plus the first times the derivative of the second. Okay, so let's go ahead and multiply all of this out. So we have 2 times 12 times negative 2x. So we have negative 48x. Right? And then 2 times negative 2 times negative 2 times x would be plus 8x squared. And then if we multiply this out, we get 144 minus 48x plus 4x squared. Okay, so if we combine like terms, how many x squareds do we have? 12. How many x's do we have? I'm not doing all the work for you. Help me out.
Negative 92.
Thank you. And then our constant is 144. Okay. The purpose of taking the derivative was so that we could use the first derivative test. Okay. So if we're using the first derivative test, Gina, what do we need to do with our derivative? Set it equal to 0. Okay. Since we have a quadratic, okay, it looks like there's a GCF. What is that GCF? And so I'm going to factor out a 12 left over. We have x squared minus 8 x plus 12. Okay. Cole, what does that factor to?
6 and 2.
Positive, negative.
Well, x equals 6 and x equals 2.
So how about x minus 2, x minus 6? So that our critical points are x equals 2 and x equals 6. Okay, now the whole point of the first derivative test is to figure out where we have minimums and maximums. Okay, so I'm going to put both critical points on our number line, but what do we know about x equals 6?
Has to be less than 6.
Okay, we know that x equals 6 can't be an answer. It's good to put it on the number line so that you test the correct intervals, but we know it's not going to be our answer. Okay, So if we plug, something in this interval right here into our derivative, what kind of value will we have? And between 2 and 6, okay, we plug in like 3 into our derivative, what kind of value are we going to have? 12 times 1 times negative 3. Negative. Okay? So Michael, what's true if our derivative switches from positive to negative? We have it. All right. Our question was, how large should the square be to make a box with as large a volume as possible? Okay. So Madison, what is the dimensions of the squares that we need to cut? If we found that 2 was our maximum, you're going back to the volume, okay? We actually don't need the volume. All we need is to know how big our squares are. So since x represents the dimension of our squares, that's all we need to know. Okay, so do you see how these squares are x by x? Okay, we found x to be 2. So our squares are just 2 inches by 2 inches. And that's all we have to do. Okay, it doesn't ask us what the maximum volume is, so we don't have to go back and plug that back in. Okay. Joe, is there an issue?
Cold and was confused.
Okay. We found x is 2 that gave us our maximum.
With the following students, please report to the competition gym for your yearbook photo. Microfinance Club, Titan Ambassadors, Education Academy, and Upward Bound Club. Again, Microfinance Club, Titan Ambassadors, Education Academy, and Upward Bound Club. Thank you.
X equals 2 gave us our maximum. They asked for the squares. Come back up to the picture. Our squares are labeled as x by x. So our answer is 2 by 2. Read through your second example. Okay. We have a piece of paper with margins, and we want to use the least amount of paper. Okay. So when we get to our calculus, are we looking for a minimum or maximum? So minimum. Okay. Good. Here is our piece of paper. What are our top and bottom margins? 1.5. So like this is 1.5. Right? And our side margins are 1. So this right here is 1. Okay. Like this is the top margin, right? So the top is 1.5. They give us two pieces of information. We want the least amount of paper used, but we also know the area of the words, right? We want 24 square inches for the words, correct? Okay, so what we can do is we can label this length right here as X, and this length right here as Y. We know that X times Y should equal what? 24, because we want the area of our words to be 24 square inches. However, we want the minimum usage of paper, right? We want the minimum dimensions. So this is what we would consider our secondary equation. Okay. First of all, we know that X times Y is 24. There's really no room to take a derivative, okay, since they gave us the number. Our primary equation needs to deal with what we're trying to find, right? We want the piece of paper that would be the least amount of paper. So this deals with words, not the entire sheet of paper, okay? So what is the area of the entire sheet of paper? What's the length of our piece of paper? Isaac, what's the length of our piece of paper? Other Isaac, what's the width of our paper? So the area that we're trying to minimize is X plus 2 times Y plus 3, because that's our entire sheet of paper. Now, what kind of function is this? It's implicit. That's not what we want. We need an explicit function so that we can use the first derivative test. Luckily, we have this secondary equation. What can we do with this secondary equation? Can we write that y equals 24 over x? Is that a fact? So then we can come back over here and rewrite our area equation in terms of just x. My suggestion to you would be to multiply this out first. Right now, we don't know a whole lot about the dimensions of our paper, but we at least know that X and Y need to be what kind of numbers? Say louder. We know X and Y need to be positive. So right now, that's about all we know, is that X needs to be bigger than 0. Okay, a negative margin is not, or a negative dimension is not going to make sense. But since we don't know how big our paper is, we can't really say much else than that. Okay, so to use the first derivative test, I think it's going to be in our best interest to go ahead and multiply this out. All right, so our area, let's go ahead and rewrite it. X times 24 over X would be an X times 3. And then we have 2 times 24 over X. And then 2 times 3. we have 30 plus 3x plus 48 over x. Okay. All right, so now we can take the derivative. What's the derivative of 30? Good. The derivative of 3x. Okay. 40 over x, we like to think of that as 48 times x to the negative first. Okay, Josie, what's that derivative? Good. Okay, so for the first derivative test, we need to set this equal to 0. Remember, it is my suggestion that if you have a negative exponent, you move it downstairs. Okay. And then what's my next suggestion? Since we have a fraction, what's my suggestion? Common denominators. So we can write this as 3x squared minus 48 all over x squared. Okay, so our first critical point comes when the denominator is 0. Where is that? Where's our denominator
The
0?
following students, please report to the competition gym for your yearbook photo. Photography club, science club, robotics, and Leo club. Again, photography club, science club, robotics, and Leo club. Thank you.
Okay, if we set our numerator equal to 0, plus or minus 4, okay, now, we know that negative 4 can't be a dimension for our piece of paper, so don't waste time testing it, but still put it on the number line so you don't pick the wrong number to test. Okay? We said that x needs to be bigger than 0. Okay? So technically, 0 shouldn't be an answer either. Okay? So let's test our derivative here. If we plug in a number outside of 4, what do we get? If we plug a number between 0 and 4. What did you say? Negative. We are looking for a minimum. There it is. Okay. Now, x equals 4 is our minimum, but that's not necessarily our answer. Okay? We want to know the dimensions of the page. Now, if x equals 4, that is this right here. So what does that mean about y? We come back to our secondary equation, we know y has to be 6. 4 by 6 is still not our answer. Remember, we have margins, okay? So we have 1-inch margins on the side. So this piece of paper really has what width? 6, and then these margins are 1.5, so this has length 9. So to minimize paper, we need a 6-inch by 9. That's not a 9. 6-inch by 9-inch piece of paper.
Do we have to write it in dimensions like that, or can we multiply it?
Do not multiply the number. I want the dimensions. Isaac, you can just refer to the video for the third example, okay? Or copy it from someone. All right, on to the last one. Go ahead and read through it. All right, we've read it. Let's draw our picture. What parabola are we working with? Oh wait, sorry, our intersector, right? 4 minus x squared looks like this. And we have, oh, no, our interceptor is a point on the screen. So 0, 2 is our interceptor. We want the closest points that come to the projectile. Now, since this is a parabola, and this point lies on the axis of symmetry, there's probably going to be how many points that are the same distance away? 2. The only time there would be 1 is if it were to be the vertex. Okay, but you could potentially have 2 points. Okay? We want the closest point that comes to 0, 2 on that equation. Okay? So first of all, minimum or maximum, Jake? Okay? So it says closest, we are looking for a minimum. We're looking for how close a point is to another point. How do we describe that length? Distance. Okay? And how do we find distance on a coordinate plane? Okay. Okay, so we're trying to find some generic point xy, and we are trying to minimize the distance it is to the point 0, 2. So we are trying to minimize the distance between xy and 0, 2.
For the following students, please report to the competition gym for your yearbook photo. Type text, debate, gaming club, and college possible. Again, that's type text, debate, gaming club, and college possible. Thank you.
Is that x minus 0 squared?
Yep. X minus x squared plus y minus y squared. Okay. Now, is this an explicit function? No, which means we need a secondary equation. Jennifer, what's one piece of information that we could use for a secondary? Is there another way that we can relate x and y together besides our distance function? Do you see anything? Cole, you're mumbling something under your breath.
Well, I don't think so.
Well, say it.
Why was you using the notation?
That's exactly right. Okay. That's another piece of information that we have that relate x and y together. Okay, y equals 4 minus x squared. Now, which variable would it be easier to substitute in for? Change, what'd you say? Somebody said something. Y. Don't solve for x and use square roots inside of your square root. We know y equals 4 minus x squared. So we can do that. Okay. So let's go ahead and simplify our distance formula here. So we have x squared, and then here we have 2 minus x squared squared, correct? Before I get too far. Okay. Here's the deal. Some of you are starting to cringe thinking about taking the derivative. Right? Taking the derivative of a square root. Okay. So let me give you a piece of advice. Or let's think about this. If we are trying to minimize this function right here, if we just take what I highlight in green and minimize that, wouldn't that make our square root minimal as well? If we minimize what's under the square root and then put it back into the square root, wouldn't that still make the square roots the smallest? Does that make sense? So in terms of easier calculus, we can say, all right, well, if I'm minimizing a square root, I know that if I minimize what's underneath, I can still get the minimum. So we're going to just take what's underneath the square root and minimize that. So derivative time. What's the derivative of x squared? Okay. When we take the derivative of 2 minus x squared, we're going to do chain power rule and then chain rule. So what we have is 2x minus 8x plus 4x cubed. Do you agree with that? So our derivative is 4x cubed minus 6x.
Are we allowed to, like, going back to D equals radical letter, can we FOIL the 2 minus x squared?
Oh, of course. You can FOIL this out and just take the derivative of a polynomial.
I did that, but I didn't get that.
You should.
Well, I mean, I
If
got
you
that.
FOILed it out, you should get x to the 4th minus 3x squared plus 4.
Yeah, well, I got 1/2 times that, and then it's not going to do that.
Why 1/2?
Because if you're taking the derivatives, if you're doing the derivative, you have to put that all over 1/2, because it's a radical.
Right, and did you hear me say that we're only going to take the derivative of what's inside? Because if we find the minimum of the underneath, then the radical will also be minimized.
Worry about this first thing.
Right. So if we set this equal to 0, we can factor out a 2x We have critical points of 0 and plus or minus radical 3/2. Okay, now, since we're talking about a point on a parabola, anything goes, right? So we do have to check all of these numbers. Okay, so this interval right here, if we plug in -2, what kind of number do we get from our derivative? We plug in -2. Negative? How about if we plug in -1? We'd have negative times negative, right? 2 minus 3 is negative. We plug in a +1, we'd have 2 times -1. We plug in this interval, we could pick 2, we would have 4 times 1. We are trying to minimize our distance, so let's go ahead and recognize what our minimums are. We have minimums when x is positive, negative, radical 3/2. Okay. Now, we need to answer our question. What are the closest points that the projectile will come to 0, 2? So we are the closest when x is plus or minus radical 3/2. We can come back to our secondary equation and plug those in to get the actual coordinates, okay? Because we want to be on that parabola. So, when we have negative radical 3/2, our y-coordinate is 4 minus 3/2, which is 5/2. And when our x-coordinate is positive radical 3/2, our y-coordinate is once again 5/2. Here are the two closest points to 0, 2 that travel on that parabola. Okay. If you ever thought, when am I ever going to use calculus to help me, this would definitely be the section where you could see it. Okay. Maximizing volume in a box. Minimizing the amount of paper used. Okay. Optimization is super awesome in my mind. Okay. All right. Your homework is on your gold sheet. Let me go ahead and stop this video.